Okay, good evening. If you're coming from the last video where we looked at saturating a transistor, we're now going to look at the BJT load line analysis. From that last video, we found a light switch, so it's a little bit brighter in the room now, but we're going to carry through with a load line analysis similar to what we did with the diode. Now we're going to flip back from our electrical symbol that we previously looked at. We're going to kind of bring back this NPN semiconductor material sandwich. Now, similar to the diode Shockley equation that applied to the PN junction, when VBE is forward biased, we can say that the emitter current is equal to this term here. We have our VBE value, we have VT, which is our thermal voltage. Now recall that VT, that thermal voltage, is 26 millivolts at room temperature. Now recall that for the emitter, we can say the emitter current is equal to the base current plus the collector current. And from that, we can introduce our beta term. Now recall that we can say the collector current is equal to the gain times the base current, which is also equal to alpha times the emitter current. Now what we can do, we can take this part of the equation here, plug in what we found up here, and we can just substitute that in. Now we can make a substitution, call it I sub s. It's going to be equal to alpha times IES. Now, this is where we get a little bit hand wavy with approximations, and we're going to compare e to the x minus 1 versus e to the x. So for x greater than 2, we make a very bold approximation that e to the x minus 1 is approximately equal to e to the x. Again, very bold approximation. But nevertheless, for VBE being greater or equal to 2 times the thermal voltage, our approximation becomes this, where we got rid of that minus 1. Now if we wanted to include alpha again, we could just break up this IS here into what we defined up here. Now if we wanted to be more precise for the emitter current in terms of the base and the collector, we could say that this emitter current right here is equal to IB, and then some collector current that's also expressed similar to the Shockley equation. From that we could find the base current, where we just get this 1 minus alpha, and then this term that we're familiar with. Now this is where we pull the input characteristic from, and this allows us to find the base current. So that's how we get this. So let's look at a circuit to actually do the load line analysis. So here's our circuit. Pretty straightforward, nothing crazy, except notice here now for the base we have a DC source and an AC source. For the collector we have a DC source that's going to be equal to 10 volts. Our DC source for the base is going to be 1.6 volts. Our resistor on the base is 40K, our resistor on the collector is 2K, and our AC source on the base is 0.4 times sine of 2000 pi t. So what we can say is that the input voltage is going to be equal to our DC term plus our AC term. And from this, we know that the input voltage is going to have a minimum value, 1.2 volts, a maximum of 2 volts, and an average value of 1.6 volts. Should be straightforward, simply from what the value of this AC term could actually be. Now, since the input voltage will vary, we would expect the base current to vary as well. So by simply going through the calculations with our value, we find a minimum base current of 15 microamps, a maximum base current of 35 microamps, and an average base current of 25 microamps. Now for this analysis, we're not going to assume that VBE is equal to 0.6 volts, but rather we're going to set up a KVL. Now that KVL around this loop here is going to include our voltage sources, the voltage drop over that resistor RB, and then whatever we're saying that VBE is. But notice, because everything is kind of time dependent, VBE is a function of time, and that's all going to be equal to 0. Now if you recall the load line analysis for the diode, we do two things. From this KVL, we evaluate what happens when that base current is equal to 0, and when VBE is equal to 0. So if the base current is equal to 0, we simply get this term here. And if we move on to the second step, where VBE is equal to 0, we get our base current to be some values, but again, notice the time dependence here. And because we have all our values defined above, we can actually plug in what these values would be. So if we consider the average, the base current average we know is 25 microamps, and that'll correlate to VBE as 1.6 volts. For our minimum, our base current 15 microamps, our VBE is 1.2 volts. And then for our max, our base current is 35 microamps with VBE being equal to 2 volts. So what we're going to have to do is draw 3 separate load lines that correspond to the average, the minimum, and the maximum. And where we have the intersection, well, we're going to have 3 different intersection points. Now what we can do is define something called the Q point, and that's going to be where that average value is and the intersection with it. Now we know for a maximum and minimum, we're going to hover in between this red and blue line along our current curve, and those intersection points will tell us what our actual base current is. And from that, we can also determine what VBE really is. So at the Q point, let's say that the base current is equal to 22 microamps and VBE is equal to 0.65 volts. At the max, it's 31 milliamps with VBE equal to 0.68 volts. The min is 14 milliamps with VBE equal to 0.63 volts. Notice here we're still within that 0.6 to 0.7 volt drop for VBE. So that's how we work with the base side of the NPN. Now we're going to work with the collector side. So we're going to set up a KVL on this loop. Simply get that VIC minus the voltage over RC minus VCE is going to be equal to 0. Now if IC is equal to 0, we simply get that VIC is equal to VCE. That's going to be equal to 10 volts. And if VCE is equal to 0, we simply get that IC is equal to 5 milliamps. So these are just setting our two conditions to get that load line. Now, just take note here, it's not required to say that we have this IC is equal to beta times IB, because we're going to look at the output characteristics. So if we do that, and we also consider the input characteristics that we found, we can see that we're going to be looking at a few different points for the base current. 31 milliamps, 31 microamps, 22 microamps, and 14 microamps. Now notice here on the output characteristic, we don't have those values. So what you may have to do is approximate where those curves would be. So perhaps the 14 looks something like this, and the 31 microamp base current right here, we can safely approximate that to be the 30 microamp line. So from the values we found up here for our conditions, that's where we're going to connect our load line. So we have 10 volts right here and 5 milliamps right here. So we draw that line that connects those 2 points. So if we note where that intersection is, it would be between these 2 points, so we know that we would hover on this line. So now we can consider what happens in a very unique case. So we noticed in this region, ignore my squiggly line, it looks awful, this would be the active region. But what happens if we consider a base current, or we had it set up such that the base current was equal to 50 microamps, and we still had the same kind of line? Well, if we look at the 50 microamp base current line, and we look at the load line, we see that that hits right before 0.2 volts. So what's going on here? Well, we know this is the saturation region. And if we had now this whole span, there would be points in the circuit where we are in the saturation region, and then we transfer over to the active region. So it's really just connecting all the load lines and seeing where you line up. Now we've done a lot with NPN transistors. In the next video, we're going to look at PNP transistors. But thank you for watching, and we'll see you in that video.